You're very welcome.
So thank you, Katya, for invitation. I am glad to have opportunity to give this talk. So the so the talk is about rigidity for the Lorentzian matrix. So short introduction. Let omega be smooth bounded domain. Consider a Lorentzian metric in the cylinder R cross omega. This is formula 1, gives you the Lorentzian matrix. Lorentzian is because the signature of matrix GJK is plus, minus, minus, minus. So denote by G upper JK, the inverse metric tensor, and denote by H, the Hamiltonian. So H is summation 1/2 JJK CJ it's the formula 2. So Hamiltonian system corresponding to this Hamiltonian is given by formulas 3 and 4. So dx dt equal dh dx, dx dt equal minus dh dx, and for x0 dx0 dt equal dh dx0, and dx dt equal minus dh dx0. This is 0 because h is independent of x0. And since from 4, because dh dx0 equals 0, dx dt equal to 0, so x0 is independent of t. The initial condition for our Hamiltonian system are x at 0 equal y, x at 0 equal eta, x0 t equal x0 is eta 0 independent on t, in time x0 of 0 equal to 0. Now, this is a well-known computation that full derivative of h in t is equal to 0. So h of xt, x0, t, xt equal h at initial points, h of y at 0, eta. The solution of this x0, x, x0, x such that h of y eta 0, eta equals 0 is called null by characteristics. The restriction of this x0, x, x0, t to the x space is called null-geodesics. We will have null-geodesics, two kinds of geodesics, null-geodesic, which is projection to x space, and also null-geodesics, which is projection on x0, x space. The later we call time-space null-geodesics. So time-space null-geodesics is projection of Hamiltonian system of x0, x space. no geodesics or no characteristics are called forward if derivative in time is positive. It follows from the equation so that no characteristic is forward if dh dx0 equal positive. Now, when we take change of variable, that if x of x hat is diffeomorphism in R cross Rn, then inverse metric tensor has the form formula 7 dx dt dx dx hat transpose g of x hat equal dx hat, formula 7 in new coordinates. So we can use this change of variable to make the inverse metric tensor in new coordinate such that the 0, 0 equal 1, g 0, j equals 0, and then the Hamiltonian system after simplification notation has the form dx0 dt equal 1, dx dt equal g hat xi, dx dt equal minus 1/2 dg dx xi dot xi, where g hat is the inverse metric tensor in new coordinates. Now, denote by L of denote by L q t y eta the integral over time space geodesics x0 equal x0 t y eta x equal xt y eta starting at point 0 y eta at t equals 0 and ending when t equal capital T at the point x0 t in x t y eta. The length of this time-space geodesics is given by integral 10. Now, this is a length in Euclidean metrics. Now, let y0 belong to the boundary d omega and gamma y0 epsilon be an epsilon neighborhood of y0 in d omega. Denote by gamma y0 the union of all time-space null geodesics in R cross omega starting on gamma y0 epsilon. So we're considering all null by characteristics x equal x of t y eta, xi equal xi of t y eta, where t is positive, y belong to this neighborhood, gamma y0 epsilon, and eta is fixed. Denote by capital T of y eta such a point that corresponding x of t y eta belong to boundary. We call this capital T y eta maximal because when t larger than capital T, the noble characteristic leaves the cylinder R cross omega. So this is what I said, that time-space, consider time-space forward null geodesics x equal x0 of t y eta, x equal x of t y eta that enters cylinder at point 0, 1 at the time t equals 0 stays in R in the cylinder R cross omega for t between 0 and capital T and reaches again the boundary of cylinder R cross d omega at point x0 t, xt, x of capital T y eta at the time t little t equal capital T. So we consider forward, null geodesics, better to say time space null geodesics.
Plus 972 52 317 4340.
So now I can formulate the main result of the talk. Suppose we have two metrics, summation in Q, P, J, K, and suppose x0 of QP, x of QP be this time space null geodesics with the same initial condition 0, x0 equals 0, x equal y, and x equal eta. Suppose gamma of y0 is the union of all time space null geodesics starting on gamma 0 of epsilon. Let T prime be maximal in Q1 metric for any y belonging gamma of y0 epsilon. Then if L of Q2 T prime y eta equal L of Q1 T prime y eta for all y in this neighborhood, and if Q2 and Q1 are sufficiently close in some norm to on this set gamma y0, then Q2 equal to Q1 in gamma y0. Note that since Q1 and Q2 are independent of x0, Q1 equal to Q2 on gamma y0 is equivalent that Q1 equal Q2 on the projection of gamma 0 on omega, where the projection consists of all null geodesics. This is null geodesics in X space in omega starting at y belonging to gamma y0. So once again, I want to clarify this formulation of this theorem, that T prime of y eta is maximal in Q1 metric for any y belonging to gamma 0 of epsilon. T prime maximum means that the time space null geodesics reaches the boundary at time T prime, and when T prime larger than, when T, little t larger than T prime, it leaves the boundary, leaves the cylinder. So for such T prime, if L2 T prime y eta equal L Q1 T prime by eta for all y, and if Q2 and Q2 sufficiently close, then Q2 equal to Q1. So this notation, clarified notation, the L Q1 T prime of y eta means the length of time-space geodesics, which starts at point y eta, and at point T prime, this is the maximum. T prime is reach the boundary of cylinder R cross omega. So it's not in the domain when little t larger than T prime. So this is why it's called maximum. So this is the theorem that if length L is a length of null geodesics, time space-time null geodesics, if the lengths are equal for Q1 and Q2, for all y is the neighborhood. And if Q2 and Q1 are sufficiently close on gamma y0, then Q2 equal Q1 in gamma y0. So once again, what is gamma y0? Gamma y0 is a union of all space-time null geodesics that starts on the neighborhood gamma, little gamma 0 of epsilon. So this is the formulation of the main theorem. So little history. There are many works on the rigidity of Riemannian matrix. That rigidity with respect to length of geodesics space in space connecting X and Y. This short list of this work, not complete, is Stefanon and Ullman, 1998, Lassos, Shredinov, Ullman, 2003, Eskin, 1998, Stefanov, Ullman, Vashi, 2016, Stefanov, Ullman, Vashi, Zou, 2019. In more recent paper, Ullman, Yang, and Zou, 2020, boundary rigidity problem for some class of Lorentzian metric is proved. We also studied the case of Lorentzian metric. The main difference of our talk is that we consider null geodesics. We also use here some ideas of work Eskin, 1998. So to describe the proof of the theorem, first start with estimate for null geodesics. So once again, let HP will be Hamiltonian. Two Hamiltonian, P equal 1 and P equal 2. Denote by Q straight line connecting these two metric Q equal Q1 plus tau Q2 minus Q1. And if you substitute this in the Hamiltonian system, we will have the Hamiltonian equation depending on tau dxdt, d tau dt equal Q prime, dx dt equal minus half partial Q1, Q prime Qx xi tau dot xi tau. And the initial condition for t equals 0 equal y and eta for all tau. This initial condition doesn't depend on tau. So this is only part of system Q prime. I want to remind you that Q prime is the spatial part of inverse metric tensor Q prime. And let we also have equation for 0 coordinate dx 0 dt equal q0 0 tau plus summation q0 j tau xi j. And suppose the initial condition is 0. And so we will study the behavior of this equation when with respect to tau. So we have two pairs of equations, one for x tau xi tau and second for x0. So differentiating in tau, we get the following equation. Yes, here is the main term is you have when after you take derivative in tau, you have q2 prime minus q1 prime times xi tau. And there is a couple of other terms and low order terms. Low order terms we will need to for estimate of remainder, but for linear approximation, this low capital O is 0. Now the derivative in xi has the same similar form. Is have a similar form, and here the principal part again q2 prime d q2 prime d dx q prime minus d dx q1 prime. So in matrix form, this equation for derivative can be written in the form 14, where Q, matrix Q, and matrix F are given by this formula. Note that F is depend on Q prime 2 minus Q prime 1, and derivative Q time pro Q prime 2 and Q prime 1 derivatives. And the initial condition for this system 14 is 0 because all x tau equal to have the same initial data for all tau. So we will write the solution of Cauchy problem in operator form is R of TF, where R of T is solution operator of equation for these derivatives. Now, what we need to what we need to prove, what we proving that maximum norm of the derivatives in tau of xi tau and x tau with weight e minus nt is less than equal than L1 norm of capital right hand side, capital F, also with weight, the same weight. Since Q prime 1 and Q prime 2 are bounded, this difference is tau times Q prime square less than equal than C Q prime Q2 prime minus Q1 prime. There's capital F is less than C times Q2 prime minus Q1 prime, and the same with derivative. So therefore, we have the following estimate. Maximum E minus T dx tau dt plus dx tau d tau less than equal supremum of 0t e to the minus nt q2 prime minus q1 prime plus the same for derivatives dq prime minus dqy prime dx x tau of t d x tau of t. Formula 18. Formula 18. So I want to remind you that there is a basic estimate for solution of differential equation of first order when you have left hand side is maximum norm of solution and right hand side is L1 norm of right hand side. So this is equation 18 is exactly this general conclusion. And weights appears because we need to suppress the low order term. So now this some explanation about the proof. So how to prove this estimate? You multiply equation by e minus 2 and t dx dx tau d tau dx tau p tau integrating t from 0 to t0 where t0 is maximum, absolute value of t0 is maximum in t, and so this is formula 19 explaining how we will do integration by parts. Also, we will use that n is large enough such that ni minus q inner products dx d tau, dx tau d tau, dx tau d tau positive, where I is identity operator. We need to use formula 20 to suppress low order term in the equation and use this integration to get the to get the main estimate, I will repeat main estimate 18, that supremum norm with weight of dx d tau dx d tau is less than N1 and L1 norm of the right-hand side. As also is written in Formula 18. We will need also for estimate of remainder, estimate second derivative in tau of x tau xi tau. So differentiating the equation for first derivative, we will get formula 21, where q where q is the same as was for first derivative. And q dq d tau and df d tau can be estimated. These are formulas for dq d tau and df d tau. And finally, we will get the estimate for second derivatives. The estimate of second derivatives less than equal estimate of first derivative square, and right-hand side also square. This is 24. This will be used in the proof. Also, we need to study the derivative of x0 tau. So this is the equation for 25 is the equation for derivative in t of x0 tau. So if you take q0 tau, q tau 0 j is given by 26. So then the derivative formula 27, the derivative of derivative in tau equal 27. You have the main term is q2 0 xi minus q1 0 xi plus other terms, and the result is the d tau x0 equal the formula 28 if you integrate in t. So if you denote by the norm of q0 2 minus q0 1 is supremum, sum of supremums, q0 j q2 0 j minus q1 0 j, then we have that derivative dx0 t dt less than equal norm, this norm 29, the supremum, plus maximum norm of first derivative. And this first derivative already have where estimate first derivative in tau of x tau xi tau. In this first derivative were already estimated in the previous formulas, in the previous. Okay, so this is the collection of results which we will need for estimates of derivative of Hamiltonian equation in tau. Now let us move to our main object, the length of time-space geodesics, x equal x0 t, x0 equal x0 t by eta, x equal x of t by eta, where x t by eta belong to d omega. This shows that capital T is final, if maximal T. So the integral of this, the length LQT by eta is given by the integral from 0 to t square root of dx0 dt square plus dx prime dt square, where let us remind that what is x of q prime. F of q prime is solution of Hamiltonian system with q prime, with metric q prime, and q prime is this summation, the matrix jk from 1 to n. So only spatial derivatives of inverse, spatial components of the inverse metric tensor. And we also have dx0 dt, which is also given by differential equation. And so if you write q is q1 plus tau, q2 minus q2, q2 minus q1, then we have that derivative of the length of geodesics in tau is equal, given by formula 32. So there are two terms, one corresponding to x, which component x is in x1, etc., xn, and second to x0, where you have x0 component. Note that dt tau dx dt is equal to, given by this formula. So therefore, you have that linear term if you have derivative in tau, for tau equals 0, it will have the following form, 33. I did not wrote in details what is the second term, but the first term is q1 prime xi of t inner product with q2 prime minus q1 prime plus low not essential terms. So therefore, by Taylor formula, LQ2 minus LQ1, this is the length of length of space, time space, no geodesics, is there is a linear term tau dl d tau tau equals 0 plus G2. G2 is the remainder. So the linear term, the linear term is 36, has a form L tau Q2 minus Q1. L is a linear functional. No, for linear functional, we have estimate 38 L Q2 minus Q1 largely equal constant L0 norm Q2 minus Q1. Norm Q2 minus Q1 is written by formula 37. It has Q2 0 minus Q1 0. This comes from estimate for x0 component and the integral supremum in tau of integral e minus 2nt q2 prime minus q1 prime, and the same for the derivatives. So this is the norm which we used. Now L is linear functional bounded in this norm. And since kernel of L Q2 minus 1 has codimension 1, we have that formula 38 L Q2 minus Q1 largely equal L0 times norm Q2 minus Q1. L0 is a constant. Now about the remainder, if you differentiated L twice, we have this formula 39. There is a second derivatives. And this is the long formula, yes. But look, the last sum is square. And first sum is maybe having derivatives, second derivative of x and x0. So estimate this 39 using the estimate of in the previous chapter about the estimate of Hamiltonian solution of Hamiltonian system. We have that estimate 40, that you have supremum of second derivative and first derivative squares first derivative 40. Now if you use what was done in previous chapter, we obtained that G2 less than equal Cn norm Q2 minus Q1. So finally we have that difference of lengths LQ2 minus LQ1 is this linear part plus G2, and G2 has estimate 41. Therefore, we can rewrite this in the following form: L0 Q2 minus Q1 less than equal L of Q2 minus L of Q1 plus Cn Q2 minus Q1 square. Formula 43. So this kind of estimate was used in my paper of 1998. So we can rewrite 42 in the form 43 L0 Q2 minus Q1 less than equal absolute value of difference of length plus Cn Q2 minus Q1 square. Now we will use essential assumption that norm Q2 minus Q1 can be made arbitrarily small. So if you have from 43, if you have 42 such estimate, and then because Q2 minus Q1 arbitrarily small, we can assume that this Cn over L0 Q2 minus Q1 less than little L0 to N. As a result, we get the main estimate 45 that 2L0 Q2 minus Q1 less than equal Q2 LQ2 minus LQ1, formula 45. Therefore, if LQ2 equal LQ1, this implies that AQ norm of Q2 minus Q1 equals 0 for Y equal gamma 0 epsilon. Now, norm Q2 minus Q1 equal to 0 is equivalent to Q2 prime minus Q1 prime equal to 0, and norm of Q02 minus Q01 equal to 0 for Y equal 0 epsilon. So this is an important piece that when you have Q norm Q2 minus Q1 equal to 0, then it's equivalent to norm Q2 prime minus Q1 prime and Q2 0 minus Q1 0 equal to 0. So Q2 prime minus Q1 prime is the norm in X variable, and Q2 0 Q1
Время вообще-то.
который еще?
Без 10.
Сейчас кончится, is the norm in X0. So if both, so what simply I want to say is that Q2 minus Q1 norm equal to 0 is equivalent to Q2 prime minus Q1 prime equal to 0, and Q2 0 minus Q1 0 equal to 0 is equivalent that both norm equal. In particular, the norm is supremum in tau, so it implies that Q1 prime equal Q2 prime at X0 and Q1 0 equal Q2 0 and X0, where X0 is null-geodesics in gamma prime Q prime metric starting at Y0 when T equals 0. Therefore, Q1 X0 equal Q2 X0. So there is, once again, if you have a prime norm equal to 0 and 0 norm equal to 0, then we will have Q1 equal Q2 equal to 0 at point x0. So Q1 and Q2 combines Q prime and Q0. So now let us x0 prime be null-geodesics in gamma. So we prove that Q1 of x0 equal Q2 x0. Now let's x0 prime be a null-geodesic starting at point y prime, arbitrary point f1 prime, and reaching the boundary at point maximum is t prime, y prime, eta. Let x prime, x1 prime be null-geodesics, null-geodesics having the same initial condition. Then repeating the same proof, we will get Q2 prime, Q2 of x0 prime equal Q1 of x0 prime. Since x0 prime is arbitrary, we obtain that Q2 prime, Q2x equal Q1x in gamma 0. So this completes the proof of theorem 1. Now we consider some global version of theorem 1, not really global, but suppose the 0 be arbitrary point in omega. Consider metric Q1 as in theorem 1. Let Z0T will be formed normal characteristics starting at t equals 0, and it will reach the boundary at some point Z1. If we continue Z0 backward from Z0 starting at point, we will reach boundary at some point Z2. Just we get forward null-geodesic starting at time minus T2 and reaching again the boundary at t equal t, capital T1. So now let Z hat equal x0, z0 be corresponding time-space geodesics. Construct a rectangle gamma 0 of t as we construct gamma y0 in the proof of theorem 1. Denote by 0 tilde this null space geodesic in Q2, having the same data at points minus capital 2, T2, capital T1 as 0, zero of t. And applying the proof of theorem 1, we get that Q2 equal Q1 in this rectangle gamma of Z2. Repeating this proof for any rectangle of the form, we get that Q2 minus Q1 equal on a dense set in omega. Since Q2 and Q2 are continuous, we have that Q2 minus Q1 equal on the whole omega. Thus, the following corollary has if LQ2 T y eta equal LQ1 T y eta for y equal d omega, and if the norm Q2 minus Q1 over any Q, no, the basic is small enough, then Q2 equal Q1. Thank you very much for your attention.
Thank you very much. Thank you very much for the very interesting talk. Thank you very much. Are there any questions or comments, please? Any questions or comments, please? Please feel free to unmute yourself. Any questions or comments, please? Okay, I have just one small question. Do you think it would be very difficult, I mean, to extend your result to the case when Q1 and Q2 depends on X naught, for example, like analytically?
Time dependent, yes.
Right, time-dependent case. At least with analytic time dependence.
Yeah. I think it's possible, but I did not. I think it's yes, but you need to do it. Yes.
Thank you. Thank you very much. Yeah. Are there any other questions or comments, please? Okay, if not, thank you very much for the very, very nice talk. Thank you very much, everyone, for coming. Thank you very much. Thank you.